Hello and welcome to the Neuroscience unit. Today we are going to start looking at the brain and all of the amazing and wonderful things about it that contribute to who we are and why we think and act the way that we do. I absolutely love learning about neuroscience and the brain, and I hope that it gives you a better understanding of all of the different processes that happen in our brain that contribute to who we are as individuals. But before we get into the brain itself, we should really dive in even closer and even smaller to look at the smallest cells that make up our brain and what they do. And so today we're going to start by looking at the neuron. Neurons are the cells in our brain that contribute to everything that we do, everything we say, everything we think. This is the communication pathways that our brain operates on. So let's take a look at a neuron here. And the first thing we need to know are all the different parts of a neuron. So we see the neuron up on our screen, and we begin where all neurons begin, and that is where messages are received. And those are received at the dendrites. The dendrite then takes that information in, and it goes down to the soma, or the cell body. This is the decision-making center of the neuron that receives this information and decides what needs to be done with it. If the information needs to be sent on to the next neuron or to muscles and glands in our body, for example, it's going to send this information down the axon, which is that whole long skinny piece there. And our axon is wrapped up in this fatty tissue that's known as the myelin sheath. And this helps the information be passed faster and easier down the neuron. At the end of the neuron, we have what are known as terminal branches. These are also sometimes referred to as terminal buttons or synaptic terminals. Think about the word terminal as in like a terminal at the airport. It's where the information is going to be sent out of. And then it's sent out into the gap, which is known as the synapse or the synaptic gap, and then it's going to be sent on to the next neuron. So this is the whole neuron and all of the different parts that are involved in the neurotransmission process. They're not the only cells in the brain though. The other cells that are in our brain are called glia or glial cells. And glial cells have a whole host of functions as well. They help guide newborn neurons to their final location in the brain. They make up the insulation that is known as the myelin sheath. It helps to clean up all the cellular junk in our brain, and it creates what is known as the blood-brain barrier, which helps keep most harmful substances out of our brain. But when we talk about how information is sent from one part of the brain to another, or from the brain to our body, or from our body to our brain, we are going to be talking about neurons and neurotransmission. An easy way to remember how neurons communicate is through a simple hand trick. If you put your hand up like this, you have your fingers, which can represent the dendrites. The palm of your hand will represent the soma or cell body. Your arm is going to represent the axon, and whatever is on your arm is going to be the myelin sheath. Your elbow is a terminal branch. So that is the full neuron. If you put up another hand, now you have two neurons. The question is, how do these two neurons communicate together? Is it like this? Is it like this? The way to remember how neurons communicate will be like this. And this is an easy trick of the hand to help you remember the neurotransmission process. Dendrites cannot talk to dendrites. Terminal branches cannot talk to terminal branches. Dendrites receive information from terminal branches and then send it on to the next neuron. So when you think about how neurons communicate, use your hands as a reference to help you to remember that. When we talk about how neurons communicate, what we are referring to is neurotransmission. Neurotransmission is how information is sent from one neuron to the next. When we talk about information being sent, what's actually being sent is what's known as an action potential, which is an electrical charge that travels down the axon to send information from one neuron to the next. So let's take a look at that neural transmission process in a little bit greater detail. We have to start with a neuron who's just sitting there, hanging out, not really doing anything. If a neuron is at rest, we say it's at its resting potential. When it's at its resting potential, we can also say that it is polarized. All neurons are polarized when they are resting. They are sitting at negative 70 millivolts. We have negative ions inside the cell that is keeping it at rest and positive ions outside of the cell. The ions inside of the cell is potassium and the ions outside of the cell is sodium. The way that you can remember that is think of a salty banana, where the salt or sodium is on the outside and the potassium of a banana is on the inside. Once information is received into the soma that tells that neuron that it needs to send that information, the gates will open up and it will allow those positive ions to enter into the cell. This is a process that is known as depolarization. The way to think about this is that a neuron that is polarized is going to be very far away from zero. If you think about the two poles of the planet, for example, are very far away from the equator. So when a cell is polarized, it's very far away from zero. It is at negative 70 millivolts. As positive ions start to enter into the cell, it's going to start depolarizing. It's going to get less polar as it gets closer and closer towards the center. So as it is depolarizing from negative 70 to negative 65, negative 60, it will eventually reach negative 55 millivolts. And when it hits negative 55 millivolts, it has hit the threshold for firing. So when it hits negative 55 millivolts, the neuron will fire and it will send that action potential down the axon to the terminal branches and will send that information out to the synapse and onto the next dendrite for the next neuron to receive that information as well. And the whole process continues kind of like dominoes. Once it gets started, there's really no stopping it. One important thing to remember is that increasing the strength does not increase the speed of an action potential. What we mean by that is no matter the intensity of the message, the neurons are still going to fire at a similar rate. As long as it hits negative 55 millivolts, the cell will fire. We refer to this as the all or none response. And once the cell fires, it's going to push that information to the terminal branches, and tiny little chemical messengers that are known as neurotransmitters are going to be released out into the synapse. Those little neurotransmitters will attach to the dendrites of the next cell and then cause that cell to fire in a similar fashion. Those little neurotransmitters bind to what are known as receptor sites on the dendrites, so that each little neurotransmitter is going to latch onto the dendrite to cause that cell to fire. Each neurotransmitter has its own specific receptor site, and we'll talk about neurotransmitters in our next video. But all of these little chemical messengers are going to fit perfectly like a lock and key onto the receptor sites on those dendrites and allow those little messages to be sent down the next neuron and onto its final location. After the process is completed, those neurotransmitters are then going to be released back into the synapse. And again, it's the responsibility of, say, the glial cells to help come in and break some of those down. Others are going to be reabsorbed by the previous neuron's terminal branches. So once they attach, they're released, some are taken away, and some are taken back up in a process that is known as reuptake. The reason why we care about the neurotransmission process is because it helps us understand how these chemicals react in our brains, so that we can understand why people feel and think the way that they do. So for example, a neurotransmitter that we have in our brain called serotonin is our happiness neurotransmitter. And so if we don't have enough of it in our brain, we're not going to feel happy. This is the biological and chemical explanation for why someone might experience depression. So neuroscientists can create medications like antidepressants, and you may have heard of them be referred to before as SSRIs. And SSRIs stand for selective serotonin reuptake inhibitors. They prevent the reuptake of serotonin so that more serotonin exists in the synapse. When there's more serotonin in the synapse, it allows it to attach and reattach to those dendrites over and over again to increase the amount of serotonin you can feel in your brain, which is going to increase the amount of positive emotions you can experience. So understanding how this neurotransmission process works helps us to understand what happens when something goes wrong in the neurotransmission process and how we can better treat it. And once the neurotransmission process is over and those neurotransmitters are broken down or taken up by the previous terminal branch, the neuron needs to reset and go back to its polarized resting potential of -70 millivolts before it can fire again. This is known as the refractory period. You can kind of think about it like flushing a toilet. If you've ever flushed a toilet and then you hit the handle again, nothing happens because the process is still taking place. It's the same thing with a neuron. It needs to empty out and fill back up again before you can start the process all over. In a neuron, this only takes about a millisecond, but it is important because the cell cannot fire until it's returned to its resting potential. The last thing we'll look at today are the 3 different types of neurons. We have sensory or afferent neurons, we have motor or efferent neurons, and we have interneurons. Sensory or afferent neurons are the neurons that take information from our body up into our brain. So say you put your hand on a hot stove, that's going to send that information up into your brain to say, oh my goodness, that hurts. Efferent or motor neurons send information from the brain out into your body. So your brain tells your body, pull your hand away so that you no longer experience that pain. Interneurons are going to send information from one part of a brain to another part of the brain. Sensory and afferent and motor and efferent can be used interchangeably, which is sometimes difficult to remember what afferent and efferent stand for because they're so similar. So I like to use the mnemonic device of same, as in I don't know which neurons are the same. S and A stand for sensory and afferent because they go together. M and E stand for motor and efferent because they go together. So hopefully that helps you remember which one sends information from the body to the brain and which one helps send information from the brain to the body. The last thing I want to talk about today is the myelin sheath, because this is the one part of the neurotransmission process that can actually change the speed of neurotransmission. The myelin sheath insulates the neuron, helping those electrical charges pass by faster and easier from one neuron to the next. And the more that you use a neural connection, the more myelin sheath builds up on the brain. And what this means is the more you use that connection, the faster and easier using it will become. And so this shows us something we learned in our memory unit about long-term potentiation, that learning actually rewires our brain, that when we practice skills over and over again, our myelin sheath becomes stronger and helps transmit information faster and easier, so that you can actually change your brain as you learn. This is a really cool finding, and what I think is so incredible about the brain is that it is not stagnant and stuck at whatever place it is right now. We can constantly change our brains as we learn more information to become stronger and better at whatever we want to focus on. It takes a lot of work, but it's not impossible to do so. Our brain is fascinating, and it's what makes us who we are, and I'm so excited to dive into this subject, and I'm so excited to look at all the different parts of the brain and all of their different functions. We'll see how it works, we'll see how it can go wrong, and we can see how we can improve our neural functioning using long-term potentiation and the plasticity of our brain. Next up, we'll talk about the different neurotransmitters, those tiny chemical messengers that are sent throughout the brain, and how they're sent throughout the rest of our body. Thank you so much for watching, and always remember, be kind to your mind.